Hello everyone, welcome back to Coders Project. Today we're solving another interesting problem, minimum depth of binary tree. So we'll take a deep dive into this problem, understand its requirements, and going to solve it step by step. By the end of this video, you should have a crystal clear understanding of this problem. Let's get started. Go ahead and pause the video and take a quick look at this question. All right, given a binary tree, we need to find its minimum depth. The minimum depth is the number of nodes along the shortest path from the root node until our nearest leaf node. So the leaf nodes for this is 9, 15, and 7, and the shortest path will be from 3 to 9. So our answer is 2. And for this one, we have 2 null, 3 null, 4 null, 5 null, and 6. So our shortest path is going to be from 2 to 6, which is basically 5. Okay, let's get into it. What we're going to do is we're going to solve this using recursion. We're going to first check if the tree is empty, then we can return 0 if because there's no depth, and then we're going to check if the node is a leaf. If it is, we're going to return 1 because it's the depth 1 from itself, and then we can recursively calculate the minimum depth of our left and right subtrees, and then if one of our subtrees is none, only consider the other part of the subtree. Otherwise, we can take the smaller depth between the left and right. Okay, let's get into it. Let's quickly take a look at our tree node class which they have provided. We have a value which is the value of our node, a left pointer to its left child, a pointer to its right child, and we have our min depth function which takes in a root and then returns an integer. Okay, let's go ahead and eliminate our base case first. So if it is not root, then we can return 0. So if the tree is empty, the root is none, so the minimum depth is 0. This is our base case, and now we can check for the leaf nodes. If the current node has no leaf or children, it's a leaf node, and the depth here is 1 because it's the only node in the path. So if not root dot left and not root dot right, we can return 1. Now we're going to get into our recursive calls for a left and right half of the tree. So if not root dot left, then we can return 1 plus our, we're going to recursively call our min depth function with our root dot right. Similarly, we're going to do it for the left one. So if not root dot right, return 1 plus self min depth of root dot left. So if only one of the subtree is present and other one is missing, or if it's none, we'll only consider the depth for the other subtree. For example, if root dot left is none, the depth is 1 in the current node plus our minimum depth of our right subtree. Similarly, if root dot right is none, we can only consider the left subtree and return 1 plus the depth of left subtree. And finally, we'll consider both the subtrees and return 1 plus our minimum of self dot, going to call the root dot left, and going to also check for the right subtree, min depth root dot right. All right, so if both the left and right subtrees exist, then we can compute the depth of both of them recursively by taking the smaller depth and then adding 1 for the current node and returning the value. Let's go and run the code. Okay, all of our test cases are passed. The time complexity for this is going to be big O of n, where n is the number of nodes in the tree. This is because we have visited each node exactly once. The space complexity is big O of h, where h is the height of the tree. This is due to the recursive call stack, and that's how we find the minimum depth of a binary tree. This problem teaches you how to think recursively and handle the edge cases effectively. If you enjoyed this video, don't forget to like, subscribe, and leave a comment for any suggestions or questions. Thank you for watching. See you in the next one.